Continuing on physical chemistry, chapter 15, we're in section 8 now. In this section, we're going to talk about the barometric formula. Now, up until now, we've been ignoring gravity and just saying that it's negligible. Now we're going to talk about exactly how much difference does it make. So, this is a picture of the Earth here. It's a big, roughly spherical, and then surrounded by a little bit of an atmosphere. Now, at any height z, there's a thin layer of atmosphere. So here's what we've got here. Let's say that we're at height z. Now there's a force holding the atmosphere up so it doesn't just fall down. And then of course there's the thickness of this layer, the differential of z. So the height of the top of the layer is going to be z plus this differential of z. And then of course there's also the force holding it down the atmosphere above it, namely. So we're going to talk about maybe one cylinder within this volume at this layer. So at the bottom of the layer at height z, we're going to have this pressure P, and then of course at the atmosphere just above the layer at height z plus dz, then we're going to have a pressure plus the differential of pressure. So the thickness of the layer, of course, is just dz, and of course differential means it's infinitely thin, and then of course, like I said, capital P is pressure. Now the differential of pressure is going to be less than 0, because remember, as height increases, pressure is going to go down. Now the differential of mass, dm, is the differential of the mass of the layer, and this is not density. Now, like I said, the force down, this is going to be gravity on the layer, acting on the layer, because it has mass. And then also the pressure from the atmosphere above. Now, A is going to be the cross-sectional area of this cylinder I was talking about, capital A. Now, the force up is going to be pressure times area. And this is the force resulting from the pressure of the gas just below the layer, because the gas below the layer is what's holding up the layer of gas that we're interested in. Now, the force down is going to be the differential of the mass times gravity plus the pressure plus the differential of pressure times the area. So basically it's the gravity, the weight from gravity, times the pressure from above. Now we're going to assume that this thin layer is under mechanical equilibrium, so which means the force up is equal to force down, which should be obvious. Our layer is not going up and down, it's just holding still. So we got balanced forces, mechanical equilibrium. So we have the differential of the mass times gravity plus pressure plus differential of pressure times area. That's equal to pressure times area. And the differential of mass times gravity plus PA plus the area times dP is equal to pressure times area. See, we just distributed the area here. So solving for the differential of pressure, we get minus dm times g divided by a, and that's going to be equal to minus g over a times dm. Now what we need to do, though, is substitute for the differential of mass. We're going to do that using the ideal gas law. So remember, the ideal gas law says that PV is equal to nRT, and from the previous page we said that the V is equal to, or no, volume is just area times dz. So that's the volume of the cylinder here. So we have N, the number of molecules, moles, is going to be equal to the differential of the mass divided by M, which is the weighted average molecular weight of air. Remember, it's made of multiple gases, so we're just going to do, a weighted average of them all together. So we have pressure times area times the differential of Z. It's going to be equal to the differential of the mass divided by the molecular weight of the air times the gas constant R times T. So remember, M is the molar mass of the atmosphere. And again, that's a weighted average. And that value is 29.0 grams per mole. So M is equal to 0.77 times 28 plus 0.21 times 32 plus 0.01 times 40. So the atmosphere is 77% nitrogen, which is 28 grams per mole, and it's 21% oxygen, which is 32 grams per mole, and this is it's 1% argon, which is 40 grams per mole. So we end up with 29.0 grams per mole. So the differential of mass is equal to pressure times mass times area over RT times the differential of Z. So we get the differential of pressure is equal to minus G over A times pressure times mass times area over RT times dZ. And that's equal to minus gravity times PM over RT dZ. Now, we're just going to say, okay, don't worry about the distance from the center of the Earth. We'll say at the surface of the Earth, the pressure is P naught. And the reason is, well, there's no atmosphere below the surface anyway, so we don't need to worry about it. And again, just for convenience, we're going to say, okay, the surface of the Earth, Z equals 0. So if our Z is equal to Z prime, then P is equal to P prime. So we have the differential of P divided by P is equal to minus G times M over RT dZ. So here we are again. Here's the Earth surrounded by the atmosphere, and we're at some height Z prime. So now we're going to integrate both sides. So we're going to have the integral from P naught to P prime of 1 over P with respect to P. That's going to equal to minus the integral from 0 to Z prime of the molecular weight times gravity divided by RT with respect to Z. Now, because we're so far from the center of the Earth, we can actually assume that gravity is roughly constant. So again, we're also going to assume for now that temperature is constant at height, which is actually very wrong, but it's not that important right now. So again, we're assuming G is constant. Because the radius of the Earth is about 6,300 kilometers. Lowercase r, of course, is radius. And 99.9% of the atmosphere is below 42 kilometers. So since 6,300 kilometers is much greater than, that's 2 greater than sign. So that means much greater than 42 kilometers. We can just say that gravity is roughly constant. So again, capital M was the weighted average molecular weight of the atmosphere. But in real life, temperature does vary quite a bit with altitude. If you've ever been in an airplane or skydiving, you probably noticed that. So the integral from P naught to P prime of dP over P is roughly equal to minus mg over RT times the integral from 0 to Z prime of dZ. See, since we're assuming that we're constant, we pulled it out. And since we're assuming it's constant, we pulled it out in the integral. And again, this is an approximation because of those assumptions we made. So what we end up with evaluating the integral, we get the natural log of P prime over P naught is roughly equal to minus the molecular, or the molar mass of the atmosphere times gravity over RT times Z prime. Now we're going to take e to that power. So we get P naught over, or P prime over P naught is roughly equal to e to the minus mgz over RT. So solving for pressure, we just get P naught times e to the minus mgz over RT. This is called the barometric formula. Now this is actually a special case of the Boltzmann distribution law. See section 9 for further details. Now again, though, this is still an approximation because those assumptions we used. That's all we're doing for section 8.